All right, now on to reactions of amino acids. And we're going to start here with Zwitterion formation. Zwitterion, it's a German word. The presence of a carboxyl group and a basic amino group in the same molecule makes possible the transfer of a proton. In a kind of internal acid-base reaction, the product of this reaction is a neutral dipolar ion called a zwitterion. So definition is here. Zwitterion is a dipolar ion that carries both a positive and negative charge. As a result, the internal of an internal acid-base reaction in an amino acid molecule, the overall net charge of the zwitterion is neutral. So if we take a look at the non-ionized form of an amino acid, which it says here doesn't exist, at least it wouldn't exist at physiological pH. Well, this part here, okay, our carboxyl group, this is the acidic portion, okay? So this part here is an acid, and you should remember that an acid is an H plus donor, okay? And then the amino group is basic, and we'll put here base, and it is an H plus acceptor. So an acid is an H plus donor, a base is an H plus acceptor. And so after the acid donates this H plus ion and the nitrogen here accepts it, we're going to be left over with our oxygen is having a negative charge and our nitrogen is having a positive charge. So Zwitter means two ions in the same molecule, Zwitterion. And since we have +1 and -1, well, if you take +1 and you add -1, what do you get? 0. Okay, so overall the molecule is still uncharged. And it says here that the zwitterion is actually what is present in solids in solution. So amino acids at physiological pH, which is around 7.35 to 7.45, are going to exist in their zwitterion form because at physiological pH, it's going to be basic enough to deprotonate or to remove the H plus ion from the carboxyl group, and it's going to be acidic enough to add the H plus ion to the nitrogen. So acid-base chemistry is what I was just discussing. The structure of an amino acid in solution varies with the pH of the solution. Now, I was talking about physiological pH on the previous slide, but it says here that, for example, if the pH of a solution is lowered by adding a source of H3O plus like hydrochloric acid, so remember, low pH, so low pH is going to be very acidic. So hydrochloric acid is a strong acid. So what's going to happen is the carboxylate group is going to pick up the proton. Remember, the proton is just H plus, the H plus ion. It's going to pick that up to form a carboxyl group. So when we have our carboxylate, at a low pH, right? This H3O plus represents a strong acid, so we'll put here a low pH. Then you can see the nitrogen isn't affected at all, but now our carboxylate becomes a carboxyl when it picks up that proton. All right. Now, remember, and now if you're saying, well, I thought you said the carboxyl group was an acid. Yes, it is, but here the carboxylate is behaving as a base because it's accepting a proton, okay? And the H3O plus is acting as the acid. Now, conversely, it says when the pH of a solution is increased by adding hydroxide, and so if we increase the hydroxide concentration, in that case, we're going to have a highly basic solution. Well, in that case, not going to affect the carboxylate at all. However, the NH3 plus, it's going to lose a proton. It's going to lose an H plus ion to the OH minus to give you water. And now you have a negative net charge, right? Because your nitrogen lost that third proton. So now it's neutral and your carboxylate stays the way it is. So conclusion is, if you take most amino acids, when they have an acidic or basic side chain, it gets more complicated. But the majority of amino acids, if your R group is neutral, if you put them in a low pH, you're going to end up with an overall positive net charge. And if you put them in a high pH, you're going to end up with an overall negative net charge. So changes in pH also affect acidic and basic side chains of amino acids. Like I told you, they're more complicated. and thus the ionic form of an amino acid exists. Thus, the ionic form an amino acid exists in is determined by the solution pH. And so, what a chemist has to do is that chemist is going to have to evaluate the pH of the solution and kind of figure out what kind of charge am I going to have. Are my basic groups going to be neutral or positive, and is my acidic group going to be neutral or negative? Now, because amino acids assume a positively charged form in acidic solution and a negatively charged form in basic solutions, there is some pH between the acidic and basic extremes at which the amino acid has no net charge. And so if you remember when we looked at our alpha amino acids, if you just permit me to draw one here, right, we have our carboxylate group here, okay, which is negative, and then we have our NH3 group here, our basic group, our amino group, which is positive. If we get to this point called the isoelectric point, the negative and the positives are going to be perfectly balanced out so that we end up with a net charge of 0. And the isoelectric point, which we abbreviate, you can see it just below, but it's pi. It says the isoelectric point of amino acids with neutral R groups are all near a pH of 6. Those with basic R groups have higher values, and the ones with the two acidic amino acids have lower values. So what you need to remember is that if you have a neutral R group, your isoelectric point, your pi, is going to be somewhere around a pH of 6. All right, so it says here, draw the structure of the amino acid leucine A in acidic solution with a pH below the isoelectric point. So I'm just going to put here for A, if we're in acidic solution, I'm going to say if we put this in H3O plus, so we'll put here low pH, okay, a pH that's below the isoelectric point. Well, this nitrogen can't pick up any more H plus ions, right? It can't pick up any more protons, but the O minus can. And so we're going to end up with our NH3 plus, and I'll draw it the way they have it. So now our carboxylate is going to pick up that proton, and now we have our isobutyl group, so we're just going to look like that. Okay, there we go. Now it says in B, what does it look like in a basic solution at a pH above the isoelectric point? So don't have a lot of space here. So what I'll do is I'll write an arrow like this, and we'll put OH minus, and we'll put here high, high pH, which we assume will be above the isoelectric point. Well, in that case, the nitrogen is going to lose that hydrogen, and my carboxylate is going to remain intact, and I'm still going to have my isobutyl group here, like that. There we go. So when we're at a low pH, you can see that overall we end up with a charge that is +1. And when we're at a high pH, we end up with a charge that is -1 overall. Now, something I didn't do with these is I didn't balance the equation, but in the first one, in A, not only would you form your carboxyl group, but after the H3O plus loses H plus, you would end up with H2O. And in the second example as well, once the OH minus accepts the proton from here, you would also end up with H2O. So now both of these equations are balanced. Okay, so moving on from amino acids to peptides, individual amino acids will bond together much in the same way any carboxylic acid and amine react to form an amide. And when two amino acids come together to form an amide bond, we get what's called a dipeptide. So a compound formed when two amino acids are bonded by an amide linkage. So whenever you hear chemists talk about peptides or peptide bonds, a peptide bond a pep oops, a peptide bond is nothing more than an amide bond, but it's between amino acids. That's all it is. So if you have an amide bond between two amino acids, we give it its own name. We call it a peptide bond. So peptide linkage or peptide bond, the amide linkage between amino acids that results when the amino group from one amino acid reacts with the carboxylate group of another. So we saw this before, that if you take a carboxylic acid with an amine and we heat that up, well, we lose water, right? We get a hydrogen and an oxygen from here and one hydrogen from here. We form water with that, right? But we also form this peptide bond, okay, or amide linkage, okay? And again, when it's between two amino acids, we call it a peptide bond. Now, before we can start thinking more deeply about peptide bonds between amino acids, we have to talk about how we write amino acids down on a page or on our screen. Now, it says here if you have glycine with a peptide bond to alanine, so this is represented by the three-letter abbreviations GLY, and then this dash in between must represent a peptide bond, so that would be a peptide bond in between the two, and then alanine. It turns out that glycine is what we call the N-terminal residue or the N-terminus. I'll probably call it N-terminus because that's what I learned when I was a student many years ago. So glycine is the N-terminus because it has the free or unreacted amino group, whereas alanine has the C-terminus or C-terminal residue because it has the unreacted carboxyl group. Now, when we write them down on a piece of paper or in prose, as you see here, um, the N terminus is always going to be on the left-hand side. So you'll notice here, N terminus at the bottom is on the left-hand side, and that's a convention. And the C terminus is on the right-hand side. And again, that is a convention. So we write them down that way all the time. So N-terminal residue, the amino acid on the end of the chain that has an unreacted or free amino group. And I'll repeat, N-terminus is on the left-hand side, and the C-terminus or C-terminal is the amino acid on the end of the chain that has an unreacted carboxylate, and we put that on the right-hand side, okay? Now, we know that this is glycine because we have two hydrogens on our carbon here, and we know this is alanine because our R group is a methyl group, and you can see that we formed a new amide bond here, but we call it a peptide linkage or peptide bond. Why? Because it's a bond that's an amide bond, but it's between two amino acids, our glycine and our alanine. All right, in the tripeptide shown, identify the N-terminal or N-terminus, the C-terminal or C-terminus amino acids. Use arrows to point to any peptide linkages. So if you're struggling to identify these, one of the things you can remember is that when you put amino acids together, it always goes nitrogen, alpha carbon, carbonyl, right? Nitrogen, alpha carbon, carbonyl, nitrogen, alpha carbon, carbonyl, et cetera, et cetera. So these are our alpha carbons like that. And so you see it here, if you just follow along, we go nitrogen, alpha carbon, carbonyl, nitrogen, alpha carbon, carbonyl, et cetera, et cetera, et cetera. And so you can clearly see the three amino acids. If I just kind of put them in brackets here, here's the first amino acid, then here's the second amino acid, and then we have our final amino acid over here like this. So you can see the peptide linkages, there's two of them. There's one here and there's one here, right? Between, right, a peptide linkage, remember that's between a carbonyl and a nitrogen like this, okay? And you can see that's what I've highlighted. Those are the only peptide bonds in there. Yes, it's a tripeptide, but you only need two amide bonds or peptide bonds to put the three amino acids together. Now the N-terminal or N-terminus is going to be this side over here. Like I said, it's on the left-hand side. So this is our N-terminal, to use their terminology. And then I'll put the C-terminal over here, C-terminal. All right. And furthermore, you can try to identify the R groups that are shown here, right? Here we have an isopropyl group, so that's a valine, right? And you can try to identify this CH2SH group, and then we have a polar neutral group over here as well. So you can try to identify those. All right, so what is a peptide? You keep hearing me talk about peptide bonds, which are amide bonds between amino acids, but what specifically is a peptide? Well, the presence of amino and carboxylate groups on the end of a dipeptide allows for the attachment of a third amino acid to form a tripeptide. For example, valine could be attached to our alanine and our glycine. to form alanine, glycine, valine, all linked together. And so a peptide is nothing more than a bunch of amino acids linked together. It's not as big as a protein or an enzyme, but I'd say, if you have three, two, three, four, five, maybe up to 10 or something like that, we call that a peptide. Okay, so we would call this a tripeptide more specifically, alanine, glycine, and valine. And again, you can try and work on your R groups here. We have the methyl group, so that's our alanine. Here, this carbon has two hydrogens, so that's definitely glycine. And then here we have our isopropyl group, so that's our valine, like that. So as I was saying a little more about peptides here, polypeptide is an amino acid polymer of intermediate chain length containing up to 50 amino acid residues. So if you have up to 50, and I don't think I'm definitely not going to make you draw a polypeptide with 50 amino acids, but if you have up to 50 amino acids, we call that a polypeptide, and you should know the definition. Then once you get past that, you get into a protein. So a protein is nothing more than, a big polypeptide is all it is. So you link all these amino acids together and you get a protein when you have more than 50 amino acids linked together. Now, if we look at the structure of a protein, let's imagine we have a protein that, let's say, has 100 amino acids linked together in it. Let's say it's alanine, glycine, threonine, tryptophan, glycine, isoleucine, et cetera, et cetera. Okay. Well, when a scientist talks about an amino acid residue, okay, the parts of amino acids involved in the peptide or a polypeptide or protein chain formed by the formation of the removal of water. So all that means is if you were to look at a protein or a polypeptide, when a scientist says an amino acid residue, they're talking about one specific amino acid in the chain, right? If I go back here, if I said, you know, let's talk about the glycine, I'd say it is a residue, okay, which just means it's one part of the peptide, okay? Or if I said, let's look at this tryptophan residue in this big protein or something like that. So that's what it means when somebody says an amino acid residue, okay? All right, so it says to use table 12.1 to draw the condensed structure of the tetrapeptide. So if you need any amino acids, I'll give the structure to you. But so remember, what I said is if you want to draw a peptide, in this case it's a tetrapeptide, remember that they go nitrogen, carbon, carbonyl. So there's the first one, then nitrogen, carbon, carbonyl, then nitrogen, carbon, carbonyl, then the last one, nitrogen, carbon, carbonyl. All right. So on the N terminus, we're going to put our three hydrogens and our positive charge. On the C terminus, we're going to put our oxygen with a negative charge. Now, on each nitrogen, we're going to put one hydrogen. So we'll put the hydrogens in here like that. And we have our four alpha carbons. So on the first one, we're going to put in our valine. So we need one hydrogen here. And remember, a valine just has an isopropyl group, like that. The next one is asparagine. And so for asparagine, we need a carbonyl and an NH2. It's a primary, what we call a primary amine. The next one is cysteine. For our cysteine, we have our CH2SH. And then the last one is our aspartic acid. And for that, we have our CH2 and then our carboxyl group. Kind of running out of space here. I'll put it like that. If you want to put the condensed form, that might be a little bit prettier. So COO minus, like that. Now it says draw the expanded skeletal structure of the tetrapeptide. So what you have to remember is that when you're drawing the skeletal structure, any R groups that are pointing up are going to be coming out towards you on a wedge, and any R groups that are going down are going to be going into the page on a dash. Let me show you what I mean. So we're going to start with our nitrogen. So we're going to start here, nitrogen, carbon, carbonyl. Then we have nitrogen, carbon, carbonyl. Then we have nitrogen, carbon, carbonyl. We do it again, nitrogen, carbon, carbonyl. Okay. We'll fill out the N terminus and the C terminus. we'll put our hydrogen on each of the nitrogens. And so, like I said, any R group that's pointing up is going to be on a wedge. So we'll put our isopropyl group like this. Any R group that's going down is going to be on a dash. So we'll put our um, asparagine here. Then we got our cysteine. So CH2, oops, can make that prettier, SH. And then our aspartic acid, so CH2, COO minus. So there we have it. Now, there's something interesting about cysteine here. It says it's the only amino acid containing the sulfhydryl group. So you guys know what a hydroxyl group. So if you change the OH to an SH, you go from a hydroxyl to a sulfhydryl group. Sometimes we call this I call this a thiol sometimes. But the SH makes a cysteine a thiol, and thiols can be easily oxidized to form a disulfide bond. So if we take two thiols, and you can see this written down here. So if you take SH and SH and you react them together, you can end up with our SS R like this, and that's called a disulfide. So all chemistry students need to know what a disulfide bond is. And thus two cysteine molecules can react readily together to form cysteine, okay, which is this disulfide compound here. And you see the sulfhydryl groups undergoing oxidation, right? Because oxidation is loss, loss of hydrogen, and we form our disulfide bond. And then reduction is what? It's gain, gain of hydrogen, like that. And cysteine or cysteine can sometimes crystallize in urine, leading to cysteine stones that are shown here. But what else is interesting, and I don't have time to go over all the details of this in a YouTube video right now, but if you've ever permed your hair or you know somebody that's permed their hair, this is the reaction they're taking advantage of here. Is what they do is they take hair, and what they do is they reduce your hair. They treat it with a reducing agent so that you break all the disulfide bonds, and then they wrap it around a curler, and then they take it back this way to reform the disulfide bond so that when they pull the curler out, it'll have that curly, it'll have the curl to it. But eventually it always goes back to its natural uncurly form.